We were just talking about constant volume things. Well, what if the chemical reaction occurs where it's open to the atmosphere? It'll have a constant pressure then, but the volume could change. So now energy can evolve as both heat and work, which makes it a little more complicated. But a lot of times we're only interested in the heat. We're not interested in the work. So what? A gas expanded against atmospheric pressure. That's not useful to us. The enthalpy of a system is the sum of its internal energy and the product of its pressure and volume. Just because I told you it is, right? So enthalpy is H and energy is E. Energy doesn't have an H in it. Enthalpy does? I don't know. I didn't make this stuff up. Enthalpy is a state function like the internal energy is, like pressure and volume are. How you get from one state to another doesn't matter. So if we look at enthalpy change, delta H, that's going to be the heat evolved in a reaction at constant pressure. Delta H is equal to delta E plus P delta V. The pressure is constant, so the pressure is not changing. Well, we learned earlier that delta E is equal to Q plus W. So now we've got Q plus W plus P delta V. P delta V, though, is equal to negative W. So now we've got Q at constant pressure plus W minus W, and those W's just very conveniently go away. And we end up with this guy down here. Delta H is equal to Q, the heat at constant pressure. We sometimes even refer to enthalpy changes as things like heats of reaction. Enthalpy and heat are very similar to each other. They're not exactly the same, but most of the time, for 1A, it doesn't matter. Yeah, there's the slide. So delta H and delta E, change in enthalpy, change in internal energy, similar in concept, often similar in value. But delta E is the measure of all the energy exchanged, the heat and the work. Delta H is a measure of heat exchanged under constant pressure. So when is there a significant difference? If you have reactions that either produce or use large quantities of gas, and you have really big volume changes, then the difference is important. Otherwise, it's not. We're not going to look at things like that. Lighters are usually fueled by butane, C4H10. When 1 mole of butane burns at constant pressure, it produces 2,658 kilojoules of heat and does 3 kilojoules of work. What are the values of delta H and delta E for the combustion of 1 mole of butane? So is burning at constant pressure. So delta H, that's not a good thing to write with. Delta H, the change in enthalpy, is equal to Q at constant pressure, the heat. Delta E is equal to Q plus W. So what are these things? This is work, right? 3 joules of work. W equals 3 kilojoules, sorry. It does 3 kilojoules of work. Is that positive or negative? It's negative because the reaction is doing the work as opposed to having the work done for it. And then we've got heat, Q of 2658 kilojoules. Says it produces that much heat. Positive or negative? It's putting out. Negative. So we identified the signs on those guys and what they were, work and heat. So delta H, that's the first one here. Delta H is just equal to Q. So delta H is this minus 2658. So we can get rid of this last one because the sign's wrong. Delta E is Q plus W. These are both negative. So am I going to end up with negative 2655, negative 3, or negative 2661? Well, negative 3 is ridiculous, right? It's going to be C. Again, negatives can be confusing. If you want to do this on your calculator, use that change sign button, negative 2658 plus, that's what it looks like on mine, negative 3, and that's going to give you negative 2661. Okay, any questions? So the signs of delta H and delta E follow the same conventions. So if delta H is positive, remember delta H is equal to Q at constant pressure. Delta H being positive means that energy is coming into the reaction. Like money coming into my wallet, this is a positive thing. That's called an endothermic reaction. Endo, like into, thermic, referring to heat. If delta H is negative, that means heat is being released by the system. There's money going out of my wallet. I have negative feelings about that. This is called an exothermic reaction. Exo, like exit. Exothermic, exiting heat. Heat going away. You may have used one of those chemical cold packs. Might have one in a first aid kit or something. You know, you sprain your wrist playing soccer or something, and they pull that out and put it on your wrist. Those have ammonium nitrate in them, and they have water, and when you activate them, that mixes. And NH4NO3 dissolving in water is an endothermic process, meaning it pulls energy in from the surroundings. Well, if that little pack is in contact with your wrist, say, it's going to be pulling heat from your wrist, and it's going to make your wrist colder. Chemical hand warmers, like we talked about at the beginning of the chapter, do the opposite thing. They have an exothermic reaction, and so when those are in contact with your skin, you feel your skin getting warmer because the reaction is giving off heat. Another example of an exothermic reaction is the combustion of natural gas. Okay, we've used the Bunsen burners, right? And they make things hot because this is an exothermic reaction. As the natural gas burns, it loses heat to the surroundings. Any questions? This is a great kind of multiple choice question on an exam. It wouldn't be formatted like this because this is like 3 questions, but identify each process as endothermic or exothermic and indicate the sign of delta H. An ice cube melting, nail polish remover quickly evaporating after it's accidentally spilled on the skin, gasoline burning within the cylinder of an automobile engine. The trick to identifying these is to first figure out what's the system and what's the surroundings. So here it's asking us about the process, the chemical reaction. we can't really observe what's happening to the reaction. We can only observe what's happening to the surroundings. So when an ice cube melts, does that make the surroundings warmer or colder? Colder. Hold an ice cube in your hand, and the warmth of your hand is going to cause the ice cube to melt, right? So my hand is losing heat. Where is it going? It's going into the ice cube. Is that exothermic or endothermic? It's endothermic, right? Because the heat is going into the ice cube. So that one's going to be endothermic. If it's endothermic, is delta H positive or negative? Positive. Money's going in. Nail polish remover quickly evaporating after it's accidentally spilled on the skin. Nail polish remover is acetone. I actually have some squirt bottles of acetone. Don't know where they went. Oh, they're in the back. If you've ever spilled nail polish remover on your skin, or used it to take off nail polish, how does it make your skin feel? Hot or cold? Cold. Okay. Because it's evaporating. So here, the nail polish remover is evaporating quickly. It makes your skin feel cold, which means your skin is losing heat. Where is it going? Into the acetone evaporating. Exothermic or endothermic? Again, this one's endothermic. And if it's endothermic, delta H is positive. Gasoline burning within the cylinder of an automobile engine. So we've got the gasoline burning, and that's going to cause temperature changes in the things around it. So does your engine get hot or cold when it's running? It gets hot. It can get really, really, really hot, right? Where is that energy coming from? The gasoline burning, mostly. So the gasoline burning, is that giving out heat or pulling heat in? It's giving it out. So then that's exothermic. Delta H then is negative. I wouldn't try to memorize delta H is positive for this and negative for that. I would just think about, okay, exothermic, heat is leaving. How do I feel when money leaves me? I feel negative, right? So delta H must be negative because heat is like money. Any questions? Yeah, I sometimes have money leaving me during lab, actually, because my daughter texts me and I have to transfer money. Right? This is constant. I'm not a mom, I'm an ATM machine. Go home and thank your mom tonight. I mean, just for letting you live. Right? An exothermic reaction gives off thermal energy. Where does it come from? The internal energy is equal to kinetic energy plus potential energy. Kinetic energy can't be the source of that. Otherwise, as the temperature would fall, and that doesn't happen. So if the exothermic energy is giving off only kinetic energy, it's going to run out, right? And the temperature will go down. We see the temperature going up. So it must be the potential energy. And this is chemical energy. Atoms rearrange during a chemical reaction. We talked about, atoms being like Lego bricks. And you take a tree and a car, and they have a chemical reaction, and they turn into a house. But you have the same number of bricks that you started with. You maybe had to put some energy, some thought into making that happen. As the atoms rearrange, some of them may lose potential energy. If they lose potential energy, that's converted into thermal energy, which goes to the surroundings. So there are weak bonds and there are strong bonds. So if you're breaking weak bonds, that requires energy, but it doesn't require very much. If you were going to break a strong bond, you'd have to use a lot of energy. Okay, think about trying to break a little twig, right? You can just snap it easy, right? Or a big branch, right? And you might hit that over your knee and regret that because it still didn't break, right? It takes a lot of energy to break the big one. What's not obvious is that when you do the opposite, when you make the bond, the energy changes the same but in the opposite direction. So if you form weak bonds, that releases a little bit of energy. If you form strong bonds, it releases a lot of energy. So in an exothermic reaction, we have weak bonds being broken. Little energy has to go into that. But we're making strong bonds, which releases a lot of energy. In an endothermic reaction, the opposite is happening. We're breaking the strong bonds, which requires a lot of energy. We're making weak bonds, which only gives back a little bit of energy. So the net result is that energy has to come in. An endothermic reaction occurs in a flask. What happens to the temperature of the flask? So we have surroundings and we have system. What is the flask? The flask is surroundings. The system is the endothermic reaction. So we know the endothermic reaction, is heat going to go into the system or out? In. If heat's going into the system, where does it come from? The surroundings, from the flask. If I'm pulling heat out of the flask, is its temperature going to go up or down? It's going to go down, right? So the temperature of the flask will fall. These questions can be a little bit tricky. You just have to stop and think about it. There's two parts, like two people in a financial transaction. Money is going from one person to the other. In a question like this, you have to identify what are the two people. What's the system? What's the surroundings? And then figure out where the heat is going. Stoichiometry involving delta H. So the enthalpy change for a chemical reaction, delta H reaction, is also called the enthalpy of reaction or the heat of reaction. That one makes more sense because it's an H. This is an extensive property. It depends on how much stuff is reacting. So by convention, because we all decided to do it this way, we calculate delta H for the number of moles in the reaction, however it is written out. So here we have the combustion of propane. Sorry, Mommy's pickled bananas. Propane. So 1 mole of propane reacts with 5 moles of oxygen. Delta H here is saying that 2,044 kilojoules of energy is given off, I get that from the negative sign, for every 1 mole of this that reacts, which would be the same as 5 moles of this. So we get a conversion factor here from delta H and the coefficients in the balanced chemical equation. So we use this to convert between moles and kilojoules. Yes. Yes, I can.
I'm confused.
Okay.
Why is it 1 mole of C3H8 is the same thing as 5 moles of oxygen?
That's a good question. Why is 1 mole of propane the same as 5 moles of oxygen? Because when this burns, 1 mole of this will burn at the same time as 5 moles of that.
Oh, okay.
You have to have both of them. So what we're doing here is, that's the amount of energy released. Here, it's like, well, we're counting the propane molecules. Or over here, no, we were counting the oxygen molecules. Well, you're going to end up with the same number. Okay? That was a great question. Any other questions? Mm-hmm.
Is that the conversion number, or is that just an example?
It's an example. This would be for this specific reaction only. And so delta H will be different for different reactions. And if you need it, it'll be given there at the end of the reaction. Also a good question. So we're going to look at this kind of generic equation here. We have 2 moles of A forming 1 mole of AA. And the heat of reaction is negative 51 joules. So what is the heat associated with the reaction of 6 moles of A? Well, how much bigger is 6 than 2? It's 3 times bigger. So if I have 3 times as much stuff reacting, what should I multiply the energy by? 3, right? So negative 51 multiplied by 3 would give us negative 153. Does that make sense? You burn twice as much gasoline, you get twice as much energy. This is giving us amount for this many moles, whatever is written in the reaction. And that is just because that's how they decided to do it. It's per mole instead of per gram. It ends up a lot less conversion factors that way. Okay. Ammonia reacts with oxygen according to this equation. So here we have our balanced chemical equation, and we have delta H for this. So this tells me that when this reaction occurs, 4 moles of ammonia reacting with 5 moles of oxygen is going to release 906 kilojoules of energy into the surroundings. So this is saying calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So I have 155 grams, and I want to know how much heat is going to be given off. Well, this is the kilojoules per 4 moles of ammonia. Negative 906 kilojoules for every 4 moles of ammonia. I picked ammonia because that's what I have information about. If they gave me a mass of oxygen, then I'd look at minus 906 per 5 moles of oxygen. But I have no idea how much oxygen is there. Is this much ammonia? So I need to find out how many moles of ammonia is that mass. So this is stoichiometry, right? It says so right up there. And where do we start with stoichiometry? Grams to moles to moles to grams. Are we starting with mass? Yes, we are. So we can go from grams of ammonia to moles of ammonia. What are we trying to find? We're trying to find the amount of heat given off. We don't need to go from moles of one thing to moles of another here, because we can go directly from any one of these to heat. So we don't need this at all. We can jump, just skip around the Monopoly board and go directly to kilojoules. 155 grams of ammonia. I'm going to convert that into moles of ammonia. And then this allows me to convert between moles and kilojoules of ammonia. Ammonia, 14.01 plus 3 times 1.008 is 17.034. Now, something that I do a lot, it's a mistake I make a lot, I forget the 4 down there. So 155 times the top, divide by the bottom, times the top, divide by the 4. It's just kind of hiding down there. So 3 sig figs, huh? Negative 2.06 times 10 to the 1, 2, 3. That's a big number, positive exponent, kilojoules. The question here asks for the heat associated with. Does that tell us which direction the heat's going? Associated with, does that tell us? No. So here, we need this negative sign. Yeah. You got a different number for what?
Your KJ.
155 divided by 17.034 times 906.
Doesn't change what you vote, but I'm just concerned because I haven't delivered it.
Oh, I accidentally, when I did this on my calculator, I got another 3 after that.
Oh.
Just, I don't know, my finger slipped or something. So yeah, it's not quite that. 2061.03. Is that better?
Oh, yeah.
Yeah, thank you. I appreciate that. The final answer is the same, but that does matter. If it said calculate the heat released by the complete combustion, would I say negative 2,000 joules? No. How much did you pay for your shoes? Negative $50. What? No, you paid 50, right? But this isn't telling us a direction, and so we do need the negative sign here. That can be confusing on homework problems because you're like, I'm not sure if I'm supposed to use the negative sign or not. So think about it. Are there words that tell you the direction? Then you just give it as a positive answer. If it's not telling you any directions, then you need the sign. Any other questions about that one? One more. These go pretty quickly. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? So we're asked about the mass in grams of butane, and we're told that we have 1.5 times 10 to the third kilojoules of heat. There's stoichiometry going on here. Grams to moles to grams. This time we're finding grams, and we'll find grams from the moles of that, but we're starting with kilojoules. And kilojoules lets us skip one of the moles. Kilojoules to moles to grams. 1.5 times 10 to the 3 kilojoules. I'm going to convert that into moles of butane. Oh, sorry, 4. Per number of kilojoules. And then I'm going to convert that into grams of butane. So the moles in kilojoules, the moles is the number of moles in the equation, that's 1, for this many kilojoules, right? So I've got negative 2658 down there. And then I have to calculate a molar mass again. .12. 58.12 grams per mole. So if I do this, I've got 1.5 times 10 to the 3 times 1 divided by negative 2658 times 58.12. And I get a mass of negative 32.799 grams. Is that okay? Can you have negative mass? No, you can't. Why did this happen? We used the sign on delta H, but we didn't think about a sign for this heat produced. If we had to put a sign on it, would that be positive or negative? It's producing the heat, it's putting out. That's going to be negative. So that should have been negative also. And now we don't have a negative mass. So that would be 33 grams. C4H10. And then it is also asking us what mass of CO2 is produced. So you could do this different ways. You could take this mass and go grams to moles to moles to grams. Or you could take this amount of energy and go kilojoules to moles to grams of the other thing. And that's what I'm going to do because it seems easier to me. So we're wanting to know about moles of CO2 now. Delta H is the same, but it's that amount for how many moles of CO2? For 4 moles of CO2, so I need a 4 in there. And then I need the molar mass of CO2, which is 44.01. Negative 1.5 EE3 times 4 divided by negative 2658 times 44.01 equals 99.345 grams, 99 grams of CO2. So chemists deal a lot with chemical equations and measurements associated with those. The volume of a gas given off, or the mass of something, or the molarity of a solution, or the energy change. And these are all variations of the path, grams to moles to moles to grams.